Good afternoon, everybody. We are Team Handicapable, and we are in charge of designing an autonomous wheelchair restraint system. So just to introduce our team, I'll start off. My name is Sean Andre, and I'm in charge of hitch design as well as prototyping.
My name is Andres Medina. I'm just doing the latch design and prototyping as well.
Hi, I'm Raymond. I do the analysis of mechatronics.
My name is Albert Sue. I'm doing the logistics and the prototyping.
So to start off, as I'm sure you are all very aware by now, Spartan Superway and Automated Transit Networks are looking to make some serious changes in the transportation sector. And Spartan Superway wants to take it a step further by also making changes to how wheelchair users interact with autonomous technology and public transportation. As you can see from the slide, the current most popular transportation securement system for wheelchair devices is what's called a WTORS, or a wheelchair tie-down occupant restraint system. And this is a 4-point tie-down system, but regardless of that, it has many inherent design flaws. The first and foremost is being that the application is really slow. It takes about, on average, studies have shown about 5 minutes to apply the system. This also adds unnecessary attention to wheelchair users in public transportation settings. And then most importantly, the biggest flaw is that you need somebody else to basically apply it. And in an autonomous pod car, there's nobody else, it's just you. So our team has designed a solution for wheelchair users to use and ride unassisted. So a couple of things that we really kept in mind when designing our system. We had some objectives. We already talked about a few, but first and foremost, we wanted to make sure that it was safe. As I mentioned, we needed it to be assistance-free, and with assistance-free came easy to use and very intuitive. We wanted it to increase securement speeds, obviously. It needed to be universally adaptable to other wheelchairs, so not just for one model of wheelchair, but for many. We needed it to be space efficient so that it wouldn't basically impede or interfere with other passengers' comfort or impede the ability for storage or vehicle capacity. And then lastly, we wanted it to be compliant with current regulations set by the American Disability Act, as well as the Rehabilitation Engineering Society of North America, or RESNA. So these are our design specifications. We ultimately decided to go with a hitch and a latch design, which we will talk more about, and it'll make more sense a little bit later in the presentation. But for our design specifications, this is what we came up with. We wanted the weight of the hitch to be less than 25 pounds. We wanted the weight of the latch to be less than 30 pounds. We needed a factor of safety of above 1.6, which was set by a previous master's student named Ezekiel Sostada, who we inherited this project from. We wanted it to withstand a crash impact. The frontal impact is set by RESNA, as previously stated. They have for WTORSs, the current standard is 20 Gs of a frontal impact, and then we kind of took it a step further by giving ourselves a lateral impact standard of about 4,500 newtons, or 4,500 newton force, which is about 1,000 pound force. And then we wanted a misalignment tolerance for the latch to be about 30 degrees on either side, and then a number of release controls being 3, both Bluetooth, manual, and emergency, just in case of total system failures. And we wanted to decrease the securement time from 5 minutes to 90 seconds. So now I will be passing you to Andreas, who will introduce you to our design and further continue on the presentation.
Thank you, Sean. So just going off of what Sean said, we've been talking about design and pretty much how we came up with it from our previous work and what is out there today. And just to reiterate, right now in most transit, there is the 4-point tie-down system, and this is a pretty nice image of it. You can see top down. Here's I'll break down this chart right here. Pretty much this statistic is showing how this 4-point tie-down system is used and also how it's not used. As you can see, there's a pretty significant portion of these charts show how there's a non-use of the actual tie-down system. So that basically means for the worst case, which is it being not used, the wheelchair user will enter the bus, right? And then they'll have the driver assist them to tie them down. But as you can see, a large percentage is that doesn't actually happen. So our this next chart that I'm showing here is also the comfort on the wheelchair user, how a lap belt would be placed over them. Again, something similar. This data is showing that it's a part of it is either not used, or it's misused, or again, it's wrongly used. So that's why our project to all of us is so important, because not only are we making this whole tie-down system sort of obsolete, but we're making it more secure, more efficient, and save time so that it's always going to be used no matter what. There wouldn't be any mistake. So going off of some design, when we were thinking about the design, how is this going to work, we went off of something similar to a hitch and a latch. Similar to a car, you attach a hitch so that another body, like a trailer, can attach to it, and both bodies are secured. We also thought about how a latch on a gate for a fence post is secured with something really simple, like it gets pushed in, and then the latch closes, and it's secure. So that's also what our previous work of the master student Ezekiel Sato, he was working on. He also did that latch sort of system and a hitch for our wheelchair. And this semester, what we decided to go on was a similar system to a car hood latch, which is what this figure is here. And we wanted to, this is our pretty much representation of our hitch and latch system for a wheelchair. I'll show you with this neat graphic how it works. So pretty much it contains of the project consists of the hitch and the latch, and altogether it's mounted onto a wheelchair. And here's a post showing that it's mounted to the wall. So here's an image of what we're currently working on, what our project is, pretty much our prime design here. Like I said, it consists of a couple of items. It'll make sense in this next video that I show, but these are the main mechanisms that work, the main parts that work with this mechanism. So first is a top lever, which will open and close depending on when the hitch comes into contact. And also an arm lever, which is the first part of contact, and an action lever, which will lock the top lever. And I'll show you what I mean in this next video. This is a pretty good demonstration of that. So in this first part, the hitch makes contact. It's a little hard to see, but there's this arrow noting the force of the hitch going into the top lever. And then from there, the action lever is pretty much locking just by the friction of it. And as you can see, with a mechanism similar to like an actuator, once you let go of that or engage it, the top lever is released, and the hitch wheelchair user is able to be off and leave the system. Let that run so you can see. So like that. Now going back to our mechanism here. In the 2D video, this arm lever wasn't shown. However, it'll make sense in our total assembly. You'll see just about coming up. Additionally, in that mechanism, there has to be something to connect it to the wall, right? So this is what we came up with. We were able to source the materials, and this is all stock materials. We were able to cut it down to size and assemble it, and this is our assembly in SolidWorks. And here's a pretty good top-down view of what the assembly looks like, you're all more than welcome to see our presentation or see our pitch in working in the next room. This is what the assembly would look like in our in a mock bogey frame, which is the frame of what the autonomous vehicles would be in. Moreover, I'd like to mention that most of the assembly was made out of metal. This is what we were able to do. These other parts we weren't able to manufacture it out of metal, preferably steel or aluminum, because of price. It would be over budget, but we were able to fit the mounting frame with all the metal components, bolts, and things like that to our budget. And I'm going to pass it over to Sean to continue this design, talking about the hitch.
So the second part of this entire securement system was the hitch portion, and the hitch is designed with three major parts. The first is going to be the hitch body, the second is the collar clamps, and then lastly is the axle clamps. Altogether they make the hitch. So this is just a brief video to kind of explain to you how the assembly of the hitch goes. So it's pretty simple. Really, it's just made from some hardware you can buy at Home Depot, and you pretty much just screw it all together, and it's fairly simple to put together, and there's really the application time is really simple. To kind of give you a better representation of how the hitch connects to the wheelchair, so you can see we have these clamps, which from the position here are back here and right there. These clamps go around the back of the wheelchair frame. They open up and then they secure with hardware. Kind of get a little zoomed in view here. And lastly, like we've been talking about, it kind of has this gate latch inspiration or mechanism. So this round member or this round bar would essentially hit the action lever of the hitch clamps, of the latch clamps. As you can see, when it's backed in here, it engages them. Then we have a set of motors back here that turn the kind of the locking mechanism that will lock the latches in place. And when these parts are 3D printed, it would resist the forces of this coming out. We also have a secondary attachment here, which is where we took inspiration from the car latch, which essentially acts as a kind of a redundancy in the system and would prevent it from further, in case of something fatal. A crash or something like that. But yeah, so it kind of represents our hitch. The current prototype of the hitch is fabricated mostly from, pretty much all from PLA, except for the hardware, which was just simple hardware from Home Depot, like I said. The bar is represented by just a threaded rod that we screwed in. And the actual hitch, if this was a real product, would be made from steel. And kind of looking into the fabrication, it's pretty expensive, so we would probably and most likely do it out of like a die-casted situation. That way we can drive the price down and make multiple units very easily. Yeah. Now I'll be passing you to Raymond, and he'll kind of talk you through our analysis.
So with the hitch, we need to figure out, can it withstand a 20 Gs? So in our case, that 20 Gs translate to 12,000 pounds. In case of, what the wheelchair's weight and the average person's weight, how much the maximum amount of weight on the wheelchair. And here, after applying FEA on our hitch, we see that, here's a zoomed in view, that the max amount of stress is around 560 megapascals, and usually it's around the bars because as we've seen previously, they're only clamping on the very small areas on the bars, so that's why the stresses here are really high if we just include just 12,000 pounds. And then if we want to get the 1.6 safety factor, these are some materials that we can, I just arbitrarily looked up, these are some materials that we can assign, and it highly depends on how you want to machine it or like how you want to create the different parts, and these are some of the materials and not all of them, and these are, and this is the approximate weight because we can't make it out of metal and we just have to use SolidWorks like their thing. For the weight of the hitch, it's about 26.5 pounds, which is over 25 pounds, and that's like approximate because since there's different types of steels like I shown previously, yeah. So I just took like the average density and just and then average it, and then we got like 26.5 pounds. For the weight of the latch, it's a lot more difficult, but we were able to get it to 24.3 pounds, which is a good thing. And then here's the video of it, the wheelchair actually backing up to it, and you can see.
Interesting.
So you hover down at the bottom.
It just goes to the
Hmm.
front slide. This won't leave. Interesting. Here, I can pull it up on YouTube actually.
Yeah, so this is our, this is the hitch, and this is the latch system, and as we slowly back in, you see a lock, and then, as you see it, okay, so first we show it, the arm levers moving to show that it is working, and then we back it in, and then we lock it, and then to show how we, release it, it would, the arm, those blue ones that we colored in, it would release down, and then we can just freely go. So, yeah.
It's also not shown in the video, but we managed to get it to work with the ESP device. So essentially, it broadcasts a wireless signal that you can connect to, and then when you go onto when you connect to it on your device or whatever system you're using, you can click open on it, and it will open the latch so that you can just leave freely. So one of the ways that we implemented one of the release mechanisms, we didn't say wireless, we said Bluetooth, but that can easily be written in code to change it over. So
Yeah, I'm gonna pass it off to Albert for the rest.
So now we'll talk about how we are meeting our design specification for we're now meeting. So one thing we found was that the way the hitch, it went over the 25 pounds. Secondly, our factor of safety is for the hitch. We did really well, but the latch, we didn't do the testing for it. And same thing with the ladder impact too. So we didn't do that. We just didn't have enough time to do it. The number of controls, we didn't do that. We didn't put the Wi-Fi or Bluetooth capability of it. There's a couple of things we did. We did meet our design specification. Is the tolerance, the misalignment tolerance. We did more than 30 degrees. We passed that. Second is the weight of the hitch, weight of the latch. If we reduce the material usage, it would be lighter, so we did really well in that. The secure time, we got time, it's less than 90 seconds, so we passed that. Same thing with the factor of safety, we did that too, and it shows in the answers. So there's several future suggestions for the successor or for the next Sergeant Super Team who would do this project. One is add sensors. So it detects the user saying we could lock in or disengage the lock. Second is the 3D print. We could consider tolerance of the hitch and latch system so that we can have a real more finer 3D print rather than that we have to like deburr something. Third is that we could make the SolidWorks file more in order, so the part file is in order, so that there's no disorder, and same with assembly. Lastly is add like a vertical adjustment so that it could adjust the height of the hitch, so that depends on the model of the wheelchair, you could.
So yeah, I just wanted to say thank you. Special thanks to really the core team, Dr. Furman, Ron. You guys have been integral in our success, and we really appreciate all your guys' efforts. I think we've all learned a lot this last 2 semesters, and you never have a final iteration, you know? So yeah, but thanks again. Any questions?
How much vertical adjustment do you have with, I mean, or can you accommodate?
We can vertically adjust it manually, yeah. We
Yeah.
can just pull it out of the wall and put it back in the wall somewhere.
No, but
Yeah.
I mean, is it plus or minus a
It's
half
really-
inch in a wall?
It's really tight. So like essentially last night we had to do a couple modifications because our hitch and our latch weren't really lining up that well. Like there was a lot of tight tolerances, so we had to lose some flanges and then change up the tolerance, but it works. It definitely, we got it to go in, we got it to lock, and then we got it to unlock, all using the ESP, and it drove off. So, I mean, it was a successful run, but yeah, it just could be a little bit, I guess I could say, more cohesive.
And then you said it can do, you did more than 30-degree misalignment.
Mm-hmm.
How much did you?
Yeah, so
were
we
you able to-
actually have, so yeah, we have we have quite a lot of misalignment. I'm not exactly sure how much was the degrees.
It's more than 30.
It's, yeah, Raymond measured it, he said it was more than 30 on both sides. So technically it's well surpassed, but I mean,
It depends on the pod card, so
Yeah.
and the wheelchair is probably gonna.
yeah, I think one of our big improvements that could be done in the future with this project, if somebody continues to iterate on it, is that there could be some type of sensors applied to both the hitch and the latch, so that it's kind of almost like a magnet where it can see what's coming in and it kind of like fixes itself to it and it puts it together. So I mean, we didn't really plan for the misalignment having to withstand this much of a force going straight, kind of like off center. So that's something that we could also plan on. But yeah, the misalignment tolerance system.
So if it starts out straight, because right now it's misaligned, right, but to the wall.
Yeah.
It starts out straight, but the wheelchair user backs up in it at an angle. Will it adjust itself to try and accommodate that?
I think it would. So this has a problem. This is with the tight tolerance situation that we were talking about. So when I designed the hitch and Andreas designed the latch, we made them at a place where they would line up, but the problem is the flanges right now are in a funky place, and so
Flanges on the
the
hitch?
flanges on the hitch, yeah, so the back parts, so they get really close to both of these bolts, and so it's like if you were to back up into this, the bar would definitely realign it. Like if it contacts it come this way, the bar would hit it and it would knock it going that way. But really the problem is the flanges would come in contact with either of these bolts, and so you need to be pretty tight on the line in order to actually get it to work. So although we didn't make the misalignment tolerance, there were some unforeseen variables that we didn't.
So if that was a flatheads bolt on the insides, and
I
would
mean,
that
to be honest,
help?
If this was either out more, if these were either spread out more or they were in tighter, or the flanges were out more or in tighter in different positions, we would have no problem. Like it would be easy, but
Can I add to you?
Please, yeah.
Yeah, I think just going off of what Sean is saying, we have it's a little. So you can see how our motors are attached on the outside of this mounting plate, right? So one of the problems or the issues is the way like we design like both the latch and the hitch. If it were to come into contact at that angle, it would like hit the motors first. It would hit this side, or it would hit something else before it actually comes in contact with the locking mechanism. So instead of it being like within the like 30 degrees as a misalignment, it would be with our current system. If instead of it being 30 degrees, it would be way tighter, something like maybe like 5 degrees. So
Mhm.
if it's anything more than that, it would hit this first, like the wheelchair would hit this and totally miss the mark.
Okay,
We met our goals separately, but we met them.
There are certain things that we were able to achieve, like, and there's other things that
Yeah.
missed.
okay.
You can ask us if we demonstrate it. You could, yeah.
Okay, any other questions for the team? Okay, thank you very much. Hooray.